What's up, guys? Welcome back to Speed, Math, and CS. So today we are going to be returning to our study of AP Physics C, Electricity and Magnetism. And today we are going to be covering magnetics or magnetic field, Biot-Savart's law and Ampere's law. So first, let's get started with magnetics. So magnetic fields, right, or B fields, are first created by magnetic dipoles, right? Magnetic poles are called north and south poles. So they will look something like this, right? They'll look something like this, right? We'll have a north pole and a south pole, something like so, right? This will be what a magnetic dipole looks like. And in fact, let me actually move this down, right? Since we are going to look at how a magnetic field looks like, right? So first, magnetic monopoles have never been found, right? So if we took this magnetic dipole and broke it into half, it would essentially, if we split it down into half, it would form two poles like so. If we split it down this axis, right? So magnetic monopoles have never been found. So thus, for the AP Physics C Electricity Magnetism exam, assume they don't exist, right? So if we break a magnetic dipole in half, it'll form two new magnetic dipoles like I showed earlier. And remember, like poles repel and unlike poles attract, just like with electric charges. And the B field around a magnetic dipole is similar to the electric field around an electric dipole, right? And electric field lines external to the magnet, they start at the north pole and then go to the south pole. And so they will essentially look like this. So if we're denoting them like this, they will essentially look like this. Look like this. Yeah. So these are how they're gonna look, right? So yeah, something like so is how they're gonna look, right? These are how the magnetic field lines are gonna look, right? So magnetic field lines must be closed loops. So essentially, if you think about it, right, because there's no magnetic monopoles, the magnetic field lines will all form closed loops. So they will be in circular shapes, right? And B fields inside a magnet point from the south to the north pole to complete the closed loop. So if we're inside this magnet, right, all of this energy that collects here, right, the magnet faces this way, right, so it completes that loop. So if you think about it, right, we can have a loop like so, where we start at the north pole, go to the south pole, and then inside the magnet, it'll go back to the north pole. This right here is an example of a closed magnetic loop. So now on planet Earth, right, the north pole of a compass points north, right? So it's attracted to the magnetic south pole of Earth. The location of the geographic north pole is close to the location of the magnetic south pole, and the location of the geographic south pole is close to the location of the magnetic north pole, right? So the magnetic field of the Earth can also be approximated as a magnetic dipole. And magnetic dipoles are the result of electric charges moving in circles. And permanent magnetic dipoles and induced temporary magnetic dipoles are a property of the object which results from the alignment of magnetic dipoles within the object. So now let's talk about the two types of magnets, right? So the material composition of a magnet affects its magnetic behavior when it's placed in an external magnetic field, right? So for this, we'll actually use text, right? So actually, let's make this not black, sorry. Let's make this orange, right? So our first type will be ferromagnetic, right? So for ferromagnetic, right? Ferromagnetic essentially means that, actually, yeah. So there are going to be two types, right? There's going to be ferromagnetic and paramagnetic. So like so, right? And essentially what ferromagnetic materials can be permanently magnetized by an external magnetic field. And the alignment of the magnetic domains or atomic magnetic dipoles is permanent. So some examples of these are, sorry, whiteboard is lagging. Give it a sec. Okay, yeah. Nickel, cobalt, and iron, right? These are three good examples of ferromagnetic metals. And then for paramagnetic metals, these are materials that are only temporarily magnetized by an external magnetic field. And the alignment of the magnetic domains or atomic magnetic dipoles is temporary. So some good examples of these are like titanium or like steel. Or no. Just take a titanium as a good example for this one. So now let's talk about our first new variable, right? Because we are getting into the magnetism aspect of AP Physics C, electricity and magnetism. So we've already covered all the electricity. So now, just like for electricity, right, we had a variable that looked something like so, right? We had E naught. Yeah. Sorry. Something like so. E naught, right? So we said that this was equal to 8.87 times 10 to the negative 9, or it had some value, right? So this was essentially the electric permeability of free space, right? So essentially what we have to with magnetism, we now have a new value, right? We have nu naught, right? So this was the permittivity of free space. This is the magnetic permeability of free space, and it's the measurement of the amount of magnetization a material has in response to an external magnetic field. So ferromagnetic materials have high magnetic permeabilities, So this is denoting the magnetic permeability. So ferromagnetic materials have a high magnetic permeability that increase in the presence of an external magnetic field, and paramagnetic materials have low magnetic permeabilities. And the magnetic permeability of materials is not constant, and it changes depending on various factors such as temperature, orientation, and the strength of an external magnetic field, right? So now we get into this part, right? Just we had an electric permittivity of free space. We have a magnetic permeability of free space, and it is equal to about 4 pi multiplied by 10 to the negative 7 Teslas multiplied by meters divided by amps, right? And a Tesla is essentially, we'll actually get into what we define Tesla, but let's first look at the magnetic force. So a moving charge in a magnetic field, right? So if we have a magnetic field that looks something like so, right? This can be a typical magnetic field, right? Let's say they're directed in this direction. And then, so let's say we have where it's directed in this direction. And then we have a charge like so, that electron that is moving through it, right? So essentially, right, the moving charge in the magnetic field will experience a magnetic force. And the variable for magnetic force looks something like this, right? FB, right? Force, and then B is how we represent magnetic field, right? And it is going to be equal to Q, which is a charge times the velocity vector multiplied by B, which is the magnetism vector, right? So if we wanted to sum up, if we wanted to find total force on the charge, right? So for example, something like so, right? Total force on the charge, this is going to be equal to the electric force on the charge. Electric force on the charge plus the magnetic force on the charge. And this is going to be equal to, remember, force equals to QE. We learned that in the electricity and magnetism, in electricity, so, or in the very first unit. So this is going to be Q E plus the V vector multiplied by the B vector. And this is going to be the cross product, right? We'll get into how the cross product looks later. And we're going to be introducing a thing called a right-hand rule in order to solve this, right? So now essentially, right, if we're looking at the magnitude itself, remember this is the cross product, right? So for cross product, remember we covered in the very first lesson, right, with vectors and scalars, that a cross product will essentially have a magnitude, right? So if we look at the magnitude of if we look at the magnitude of this force B, right, it is going to be equal to QVB times sine theta, right? The direction that the charge is pointed in, multiply the magnitude of the direction of the charge is pointed in times the like magnitude of the magnetic field times the direction between like the charge and the magnetic field. So for this, right, so it'll look something like so, right? So now if we analyze this, right, we can actually determine what Teslas are, right? Remember, we introduced a unit called Teslas up here, right? We said that is Teslas times meters over A. And Tesla is actually the unit we use to define magnetic field. So if we can actually use this equation to derive the units for Teslas, right? So let's say if we isolate B over here, right? So if we isolate B over here, B is going to be equal to the magnitude of force divided by QV sine theta, right? So if we look at this, right, B is going to be in Teslas, right? So B is going to be in Teslas, right? And force is in newtons, charge is in coulombs, and then velocity is in, sorry, the whiteboard is so laggy sometimes. Velocity is equal to meters divided by seconds, and sine theta, because we covered in the first lesson for unit analysis, that doesn't have any units, right? So now, if we simplify this, remember, we have a coulombs divided by seconds in the bottom, so we have that it is equal to and newtons divided by amps divided by meters. Something like so, right? So yeah, this is the Teslas are equal to newtons divided by amp meters. So that is our unit for Teslas, right? And yeah. So now let's or actually, okay, this is actually important, right? Because like I think this appeared one time on the AP exam, but just know that like this is a very stupid concept, but like 1 Tesla, dude, the whiteboard is, yeah. 1 Tesla is equal to, there's also another way for determining, which is Gauss, right? Because of course, we don't have enough units already, we need more. So yeah, 1 Tesla equals to 10,000 Gauss, and hopefully that shouldn't appear on the test, but yeah, 1 Tesla equals to 1,000 Gauss. And that's how you pronounce that G. So now let's go on, right? So right now we've already talked about the we've already talked about the magnitude of this force. So now in order to determine the direction, in order to determine the direction, right, what we are going to do is we are going to do a right-hand rule. So for this, we actually get up and move a little. So this is like one of the first, this is the first time we've ever done this in a lesson. But essentially for this, right, what the right-hand rule is going to do is, what you're going to do for this, right, is typically when we're determining the direction, right, we're gonna have a cross product. So first, I'll show you like 2 ways to show, like, the first symbol is going to look like something like this, right? This means that that vector is coming out of the screen. So if it says this is like, if this is like the force of like FB, for example, if this is the direction of this vector of force, right? Yeah. So if, for example, we have a dot coming out, that means that vector is coming out of the screen, right? And then for yeah. And then the other notation is that if we see like an X, like so, like if I draw out an X, like so, right? This means that it is going into a screen. So think of it like the arrow, like an arrow, right? The back is sort of like the feathers and stuff that you see at the back, and then the front is like the tip. So if you see this dot, that means that it's saying it's coming out of the screen right at you. And if you see this X, that means it's going into the screen. So now let's consider this, right? Let's say that we are trying to determine the direction of a charge, right? So let's say the charge is moving in. So let's say we have a magnetic field like so, right? Sorry, dude, whiteboard's so laggy sometimes. Yeah. Let's say we have a magnetic field in the direction like so, right? This is the direction of our magnetic field, right? And essentially, so now let's say that we have a positive charge moving in the direction like so, like velocity vector is so, right? So essentially what we're going to do, and it's going to be hard to model this because it's whiteboard, but essentially what you are going to do, right, is you are going to start, like for the right-hand rule, we are trying to determine the direction of the force that the magnetic field is going to apply. So the electric field is the direction that this electric charge is going is pointing this way. So what you are going to do is you're going to take your right hand and then point it to the right. So your right hand will, oh my God. Yeah, so your right hand will look something like this, right? So you'll be pointing in the direction of the velocity, right? And then what you'll want to do is then now you will want to curl, or why did a ruler open up, right? You want to curl in the direction of the magnetic field, right? So I'll try my best to draw this, but essentially your hand will be, oh, what the, but essentially if your hand's gonna be like this, and then we're gonna curl it in the direction of the magnetic field, right? And then your thumb, right? Your thumb is essentially going to be pointing like out of the screen, right? When you do that, like do that and then curl towards the magnetic field, your thumb's going to be pointing out of the screen. So the direction your thumb is pointing is where the actual where the magnetic force is going to be. So in this case, we will use a dot like so, because our thumb tells us it's going to be coming out of the screen, right? So, yeah, something like so. So let's actually do more practice with the right hand rule, right? So, yeah, we determined that the force is going to be something like so, right? So I know this isn't a great dot. Just look at this. This is how it's supposed to look, right? But now let's do another practice problem. Let's say this time we have a bunch of, let's say the magnetic field is like so. We have a bunch of X's, right? Actually, just so we don't confuse, just so I don't confuse you. Let's say we have so the magnetic field is going to be like so. Right? Let's say this is our magnetic field. Right? So we'll say this is B in the direction, right? And then now let's say we toss a electron. Yeah. So now what we're gonna do is we're gonna essentially put the velocity, right? So velocity of the electron is pointing this way. We denote it with the vector like so. So now, in order to determine it, we're going to, once again, our fingers are going to point, we're going to point our whole right hand. Take your right hand, essentially you'll point it like that. You'll point it down this time, right? So then it's going to, your right hand is going to essentially be like this, right? And then your thumb is like that, right? Your thumb, and then it's going to be like that, right? You're going to point it like this. And then now you're going to curl in the direction of the magnetic field, right? So if we think about it, right, it's going to be like this. If we do this and then curl into the screen, I know that is way farther than I know that does not look like a hand at all. I'm trying my best to draw this, but yeah. So let's say we now do this, right, and then curl it into the screen like so. Our thumb is pointing in this direction, so this is going to be our thumb's pointing here. So this is going to be the direction of force. So do some more practice with this. I know my hand drawings are not the best, but I guess you should get the point, right? Essentially, you're going to be pointing your fingers in the direction of the velocity of the electron. You are going to curl your fingers towards the magnetic field, and the direction your thumb points in will be the direction of the force that it does, right? So even like in this example, it's been horizontal, but now let's say we had something like this, right? Where we had the magnetic field at an angle like this, and then it was pointing the velocity was still pointing like this. Your hand, right? It's going to point in this direction, right? Curl in this direction, right? So it's just going to be like not curled. it's just not going to be curled like as much, right? So if you point it like, for example, down and then to the right, like so, right? It's just going to curl like in. So it's just going to curl into the screen, right? So then if you point your hand like this, curl it like this, your thumb's going to point into the screen. So then we will have an X, and this is going to be FB, right? Like so. It's going to just go into the screen. So hopefully this should give a good idea of how to use the right hand rule, right? So now let's actually move on to, so essentially, right, so now let's go on to the idea of a mass spectrometer, right? So it's actually, so now we're going to go on to the idea of a mass spectrometer, right? And essentially what this is going to be is that, let's take this, actually like expand this a little, we're going to do a mass spectrometer, right? Essentially what a mass spectrometer is that there's going to be a velocity sector and a deflection chamber, right? So it's going to look something like so, right? Where we have and then we're gonna have like so, right? And then we're gonna have the deflection chamber like so. The deflection chamber, right, is gonna be here, and the velocity selector is going to be right here. So then essentially what's going to happen is that so the electric field is going to be pointing this way. Very obviously, this is going to be the direction of the electric field, right? So this essentially, now that we know this, we can draw the direction of the magnetic field, right? Oh, what? I don't know, it's up here. So then, so if we draw the direction of, so all the electric field is going to look something like this, right? And the magnetic field is going to be going into the screen like so. Like so, right? So essentially what this means, right, is that if we send an electron, right, let's try to determine the direction it will go, right? So if we send an electron in like this, right? So the electric field will pretty obviously push it into this direction, right? So it's already starting by heading into this direction, right? In order to determine the direction that the force of the velocity will do in, we point our fingers to the right in the direction of the charge like so. We'll point to the right, curl it in the direction, so we curl it into the screen like so, and our thumb will be pointing up. So this means that the force will be acting like so. And essentially by velocity selector, right, because this is dependent on the actual velocity of the charge, while the electric field is constant, because like, if you think about it, right, if the FB was greater than FE, then it would go up, right? It would deflect up in this and just get collected around the top. If this was less than this, it would get collected around the bottom. So because of the magnitude of FB is based off of the velocity, only positive charges at a certain velocity will actually make it through the velocity selector. So that's actually why it is called the velocity selector, right? It's called the velocity selector because it just selects a very specific velocity. So now, okay, actually before we move on, right, let's do some quick So yeah, so let's actually do some quick things regarding the wire before we get back to the mass spectrometer, because now we have to get into the deflection chamber after this, right? But essentially, next thing we're going to be covering, right, is what if we have a series of charges all moving in the same direction? So this is going to be like, for example, if we have a current carrying wire like this, and then let's say this is a wire, right? And then we have a bunch of charges all moving in the charges moving in the same direction, right? So essentially the current in a wire, right, what we derived from unit 4 was that the current in a wire, right, is equal to the number of charges, right? So is equal to the number of charges multiplied by the A, which is area, right? Multiplied by drift velocity multiplied by charge, right? Or sorry. This is it is area. But now essentially what we're going to be considering, right, is that now we have a magnetic force on a moving charge, right? So remember that magnetic force in FB will be equal to the charge times the velocity vector multiplied by the magnetic field vector, right? So let's try to find the net magnetic force acting on all charges moving in the wire in this B field, right? So the charge carrier density, or number of charges, right? So N is number of charges divided by V, right? So NV equals to NAL, right? So because of this, right, well, we can replace so the current will actually, so the current so the force will actually be equal to the force through this will be equal to QV multiplied by B going in this direction, multiplied by number of charges, multiplied by A, multiplied by L, right? And essentially, if we simplify this, it is going to essentially NAL, it is going to simplify into the into NAVQL, and we'll put the vector on the actual L because we're gonna use differential line segment, right? So so something like so, right? Multiply and then cross producted with B, right? So what you'll notice here is that we can replace this whole thing with current, right? So essentially this whole thing can be replaced with current, something like so, multiplied by magnetic field, right? And this is, we can also write this in integral form, right? If we write it in integral form, right, it's going to be I multiplied by DL multiplied by B going in this direction, right? So something like so, right? So then the direction of force, right? The magnitude of force, FB, right? Magnitude is going to be equal to ILB sine theta, right? And because it's sine theta here, because we're using cross product, right? And the direction you can determine using right hand rule is the direction between the L, like length, and the magnetic field, right? We'll do the same thing as we did with velocity and magnetic field, where you'll determine the direction of their cross product, right? So yeah, the defining direction is still the same. So now let's get back to the mass spectrometer, right? So essentially, because of this, right? We're gonna have the velocity. Yeah. So if we derive an equation for this, right? We have that V B sine theta, right, must be equal to QE, right? Because then only then will it actually pass through the mass spectrometer, right? So now if we cancel it from both sides, we get that VB sine theta, and then in this case, the direction between the velocity and the magnetic field is 90, so sine 90 equals to E, right? And then, so then velocity will be equal to electric field divided by the magnetic field, right? So because of this, right, we'll actually move this because we have to actually do the deflection chamber, right? Just we have space for the deflection chamber, right? We will now, the thing is, right, because we will now only have the B field present, right? Because the velocity selector will essentially select that specific velocity. It'll cherry pick this one velocity and send it through, right? So then now the only force acting on the charge is in the deflection chamber, right? We don't have any electric field, right? All it's gonna be is a bunch of X's, right, with the magnetic field. Right? And essentially what this is going to do, right, is all of the right? And yeah, so this is going to be equal, this is going to essentially, they're just going to deflect in like so, right? And this is going to actually have some radius r, right? But this is going to be the magnetic force acted on this charge, right? Like so, right? It essentially, now what we will do is we will use we'll use our formula, right? So we'll take our magnetic field, right? In this case, right, we just have a magnetic field. It's the same. And it'll be Q times V times B times sine theta, right? So it'll look something like so. B times sine theta, right? Times sine theta, which is going to, in this case, right, the direction between velocity and magnetic field, because it moves in a circle, even though it's moving in a circle, it's moving in a plane that's always perpendicular to the actual magnetic field. So it's just going to be sine 90, right? So, and this, yeah, so this is going to be equal to the mass, determined mass times the velocity squared divided by r, which is the radius, right? And then we can cancel out, because the sine 90 is just that, and we can cancel out one of the variables, right? This is going to be mv divided by r, right? So then now we know that velocity is e divided by b. We know that this velocity we can replace with e divided by v. So, because we determined that earlier, right? The velocity selector selects it in e divided by b. Sorry. E divided by b. Right? And then in this case, our goal is if we can isolate this, move all the other variables to the other side. So it'll become me equals to qb squared multiplied by r, right? And then essentially now this is going to simplify into so that this is going to become m divided by q equals to radius multiplied by b squared divided by e. And so the mass spectrometer is a tool for determining the mass to charge ratios of electric charges with known velocities, right? So now let's actually get into the other stuff. So we've covered the magnetics, plenty of magnetics. Yeah, so it's like almost 40 minutes of straight magnetics. So now let's get into the Biot-Savart law, right? And so this law is actually experimentally determined, so we can't actually derive this. So the only way to actually know this is just to memorize it. So the Biot-Savart law essentially tells us that if we have a differential piece of the magnetic field like so, it is equal to mu naught divided by 4 pi multiplied by I dl times r in a vector over r squared, right? And r is essentially a position vector which points to the location of the infinitesimal length of wire dl and to the location of the infinitesimal magnetic field dB. And r is the magnitude of the distance between the two locations, right? Remember, mu naught is the magnetic permeability of free space, which is 4 pi times 10 to the negative 7 teslas multiplied by meters over amps. And the Biot-Savart law shows that the current carrying wire creates a magnetic field because current is composed of individually moving charges, but even a single moving electric charge causes a magnetic field, right? And remember that the right-hand rule for magnetic field caused by moving charges, right? Fingers point in the direction of the current / wire, or DL. Fingers curl in the direction of R, which is this vector, right? And then for conventional current, thumb will point in the direction of the magnetic field, right? Or this cross product direction will be the direction of the magnetic field, like so. So if we use the Biot-Savart, so essentially, if we have a wire like so, right? If we have a wire like so, right? A DL could be like, this is an infinitesimally small portion of the wire, could be DL. I don't know why I made that arrow so big. But yeah, sorry. This is DL, right? That could be a portion. So if we, for example, take a dB, right? The dB will always be, the dB in this case, right? We fingers point in the direction of the current, and then we could use the alternate right hand rule, right? So our thumb can point in the direction of the current, and the actual magnetic field will be in the direction our thumbs curl, right? So now if we have like whiteboard is so laggy sometimes. Yeah. So if we have our hand like so, right, with pointing like this, right, and our thumb can actually so it will point in the direction of the current, and then our right hand will curl in the direction of the actual magnetic field movement. Magnetic field like so, right? And so in this case, right, R is the distance between the current like so, so it's the distance between like so, and the R vector is the direction in which it is pointing, right? So the R will be that, and the direction in this case will just be like pointed up like so, right? And then So yeah, so this is how it'll look, right? And essentially, right, the for an infinitesimally straight current carrying wire, there are infinite number of DLs, and all their dBs add up to cause the magnetic field to have a uniform value at a distance r straight out from the wire. And as the magnitude of the wire decreases as r, the distance from a wire increases, right? So the Biot-Savart law, right, can be used to determine can be used to derive our function for the actual like magnetic field a distance r from the wire, right? So essentially, if we have a circle like so, right, of magnetic charge, right? Like let's say we have a charge in the center, right? So yeah, let's say we have a charge in the center like so, right? And then we have the magnetic field, right, curling like so. It'll go like around like so, right? This is going to be the direction of the magnetic field. Like so, right? This is going to be direction of magnetic field. If we have the current going in, right? This is going to be a wire. So technically the current is going in, but if you think about the wire, right, it's like pointed towards us, right? And then we know the magnetic field around that, what it is. So what our Biot-Savart law can tell us, right, is we can actually, we will actually derive let's try to find the actual magnetic field caused through a point from like a distance r, like let's say here, right? So in this case, right, and let's try to find the magnitude, right? Direction will be pretty obvious dependent on where we are in the actual circle, right? So, well, actually, okay, no, direction is always like to the left, or technically, right? So like if we're put these in a straight line, it's always going to be towards the left is where the magnetic field is going to force you, right? So here's the thing, right? So then what you can do here is we will essentially take the fact that so our Biot-Savart law, remember what it is, right? It's dB, right? So now let's actually integrate it. Let's actually integrate it. So it's going to be B equals to mu naught divided by 4 pi, right? And then if we integrate the top, IL, right? IL R vector, right? All over r squared, right? So sorry, dl times r. So then now we can take so sorry, yeah. So if we do an integral now, right? So we took the Biot-Savart law. So let's say we do an integral, right? We have the current is constant. So in this case, we can take the current out, right? And so the DL in the direction of the r vector, in this case, we can just make this into a dr, right? So in this case, yeah, we take the I out, right? And this is going to become a if we take the integral of this, right, it's going to become B equals to, it's the same stuff that we had up here, mu naught I over 4 pi, right? But now we're gonna take the integral, so it's going to be we're gonna multiply 2 over r, right? So then it is going to be yeah, 2 over r. Yeah. So then if we simplify that, right, we'll get to the formula, this formula, right, where the the magnitude of the magnetic field is equal to mu naught multiplied by the current over 2 pi r. So this will essentially be used in the circular loop And on the actual AP exam, you're expected to quantitatively determine equations for magnetic field caused by current carrying wire in symmetric situations such as long, straight conductors or segments of circular loops. So now what we're going to cover is going to be the last thing for today before we go, right? We are going to be covering Ampere's law, right? And in this case, right, it is the mathematical equivalent to... It is going to be the mathematical equivalent, or why did I say mathematical? The magnetic field equivalent to Gauss's law, right? So Ampere's law, right, is going to look something like this, right? The closed surface integral of the magnetic field times ds equals to mu naught multiplied by current enclosed, right? So essentially what this is going to be, right, is let's actually do an example, right? Because this is very similar to something we have seen before with Gauss's law, right? Gauss's law was our fun rule that we used, right? So now let's, what we can do is we will, so let's say we have, so let's determine the magnitude of the magnetic field outside an infinitely long straight wire with radius r and current I. So what we will do in this case, right, is we will essentially have a wire like so, right? It'll look like a point, but it's let's say it's coming out of the screen with like so. So if we use our alternate right hand rule, point our thumb in the direction of the current, which is outside the screen, and curl our hands will curl sort of counterclockwise, right? So this is going to be the direction of the... so the direction is going to be counterclockwise. So now what we can do is we can draw an Amperian loop, right? So... Sorry, it's not completely the circle. So we're going to have an Amperian loop like so, right? And essentially, because we know that it's going counterclockwise, like so, counterclockwise, we are going to have a... We are going to have the... we're going to have the magnetic field pointed this way. And in this case, ds is also pointing this way, right? And then in this case, right, this distance is r, right, is the radius. And then, so it'll look something like so, right? So if we actually solve this further, we'll notice that the direction, this is the dot product, right? So this is going to be b ds cosine theta, right? So because cosine theta is 0, because they're pointing in the same direction. So it's just going to be b ds, right? So b ds, right? And actually, the good thing here is that we took an Amperian loop. And the loop is in the same direction as the side. Remember, so it's like the side vector of the Amperian loop is going to be the direction that our Amperian loop is in. And luckily, the magnetic field is in the same direction. So if we simplify this dot product, right? So if we simplify this dot, oh my god, it's horrible integral. Ignore that, but it's horrible. B ds cosine theta is just 0, so it's or 1 in this case, equals to mu naught, right? Current enclosed in this case is just the I, right? Because that's the current, right? That's gonna be current enclosed. And then that's gonna be current. And then now we can take the magnetic field is constant, or at least the magnitude of it is constant. So we take it out, right? This we can take because the integral of a differential is just the side itself. So this is equal to mu naught of I, right? And S is essentially the circumference of our Amperian loop. So if we actually we divide this by S, right? And so we'll divide it by S like so. And in this case, right, S is actually going to be equal to 2 pi r, because that is the circumference of our Amperian loop. So if you look at that, we have just derived the formula for the distance away from the we have derived the distance, like we've derived the same formula as we did for Biot-Savart law for the distance of a point charge, the magnetic field caused on it, a distance r away. So it's the same formula, right? And in fact, Ampere's law is, we'll talk about Maxwell's equations. This will be our 9th unit, right? And so Ampere's law is actually Maxwell's 4th equation in his 4 equations, which fully describe electromagnetism, right? And for the AP Physics C Electricity Magnetism exam, you are responsible for using Ampere's law only in situations of high symmetry. So for example, if we have a long straight wire or a solenoid and or like conductive slabs or cylindrical conductors containing like wires or solenoids with conductive slabs, cylindrical conductors containing a current density, right? So next time, right, that is going to be the end for today, right? Our next lesson, unit 7, is we're going to be talking about Faraday's law, Lenz's law, and we're going to start with solenoids. So we're going to talk about solenoids, Lenz's law, and Faraday's law. So I hope you enjoyed this lesson. Be sure to drop a like, drop a sub on the video, and hopefully this was a good explanation and you guys understand this topic now. So we'll see you in the next one.